Hello, everybody. Thank you for joining us to this webinar. I'm delighted to welcome Nikki Freeman today for this webinar entitled Individualized Treatment Rules, Characterization via Surrogate for the Value Function. Nikki is actually assistant professor at the Department of Biostatistics and Biopharmacie at Duke University and at Duke Clinical Research Institute in Duke University. And she did his PhD with the world famous Michael Kozorok at the University of North Carolina. There are two area expertise, statistics and dance, but it's much more easier to do a webinar on statistics than dance. Her research is dedicated to developing practical methods and evidence for health and healthcare with a statistical precision medicine framework. And the webinar is organized by the SFdS Biopharmacie and Healthcare Group. If you have, Nikki will answer to some questions at the end of the talk. So thank you, Nikki, for giving us the opportunity to learn a few things about precision medicines, and I'll let you the floor. Thank you.
Thank you. Thank you so much, Nicolas. It's really great to be with all of you. I am just going to share my screen so you can see my slides. So the title of today's talk is Individualized Treatment Rule, Characterization via the Surrogate for the Value Function. And we're going to talk about what that means in a little bit. But first off, we're going to start with an introduction to precision medicine so that we can lay down some vocabulary and also just kind of learn like what is the precision medicine framework. And then I'm going to try to give you the explanation for why I did this work and like what interests me specifically in precision medicine. And then we'll talk about the actual method itself. Okay, so, whenever I was a brainy graduate student, I just arrived in Michael Kozorok's lab and, everyone's doing precision medicine and it seems so cool. Precision medicine, Michael Kozorok and Eric Glaber wrote in 2019, is the paradigm wherein patient heterogeneity is leveraged through data-driven approaches to improve treatment decisions so that the right treatment is given to the right patient at the right time. And whenever you hear this, you think, yes, that is exactly what I want to do. I want to know how to give the right treatment to the right patient at the right time. It's a, really great thing. But, and it's a beautiful quote, but it doesn't tell us exactly like what to do or how we're going to do this. So, mathematically or like rigorously as a statistician, we need to be able to write this in math. So I'm just going to pin this quote up here at the top, and we're just going to walk through it to kind of understand when I say precision medicine, what exactly am I talking about? Or like, what is my flavor of precision medicine as a statistician? Because certainly precision medicine, there's many methods in it, and it really ranges from like very mechanistic understanding of disease and pathophysiological processes all the way to, these very data-driven approaches that I work with. So thinking about precision medicine, this is kind of the way we're going to work with it is using this quote from Kozorok and Glaber and then formalizing it mathematically or statistically. So we're going to need just a little bit of notation. We're not going to do too much, but we're going to let A denote treatments. And just for simplicity, we're going to assume that treatments are either 0 or 1. So binary treatments, very, very simple setting. We're going to assume that our outcomes are denoted by Y, and we're going to assume that bigger is better. Of course, if you're in the setting where smaller is better, you can just flip the sign. No problem there. We're going to have some patient features, which are just going to denote by X, D-dimensional. And then we're going to have these potential outcomes. So if you're familiar with biostatistics and causal inference and these kinds of things, you've met potential outcomes before. But if you don't know them, this Y with the 0 inside it is what would have happened if you had received the 0 treatment. And the Y with a 1 inside of it is what would have happened if you had been given the 1 treatment, okay? And so, of course, if we're trying to pick the right patient the right treatment for the right patient at the right time, in an ideal world, I would know exactly what would happen if I gave you the 0 treatment. And I would know exactly what would happen if I gave you the 1 treatment, and then I would just compare. But of course, we can't do this, right? I can't know what would happen if I gave you both treatments. I can only give you one at this exact moment, at this exact point in your disease process. We can only see one or the other. And this is the fundamental problem, or the fundamental issue in causal inference, is that it's a missing data problem. I can at best observe one of these. What happens if I were to give you treatment 0, or what happens if I were to give you treatment 1? So the great thing about causal inference, and this is really what like where do we go from here, is instead of being able to do this for individuals, since I can't see both, what we can do is we can look at things on average. On average, what would have happened if I had given everyone in the population the 1 treatment, when compared to if I had given everyone the 0 treatment. So that's just the average treatment effect. So again, if you've been in causal inference or been in biostatistics, this is something very familiar to you. Similarly, we can do the conditional average treatment effect, or the CATE, where we look at what would have happened on average if we'd given everyone treatment 1, compared to what would have happened on average if we'd given everyone treatment 0. And then we're just conditioning on people that have a particular set of covariates. So big X equal to some specific little x. And so that's the causal inference lens. This is how we kind of think about decision making, if I'm trying to decide to give people 0 or 1. But this is imagining what if I had given everyone the exact same treatment. And the goal in precision medicine is we think we could do better if we tailor treatments to individuals. What if I could look at your observable characteristics and better match you to treatment? So the whole center of this is getting the right treatment to the right patient. So we need to be able to go from patient features to treatments, some kind of mapping that takes me from these features that I can observe to a treatment. Well, a mapping is just a function, right? And so that's what kind of the whole universe, or a lot of our focus is going to be on, is learning these functions. And I'm going to call it an individualized treatment regime and denote it by the letter D. And it's just a mapping from patient features to a particular treatment recommendation. You will also hear people, and sometimes even myself, I'll say dynamic treatment regime, or policy, or treatment recommendation. There's all sorts of kind of language that people use to describe these things, but at the end of the day, they're all talking about these kinds of functions. Now, of course, we need a way to know, how did I do? What would have happened if I were to follow this particular treatment rule? What if instead of giving everyone treatment 1 or giving everyone treatment 0, I had followed what this function says, where I put in the patient features and I get a recommendation out? And so what we can think about is something called the value of an ITR. So we have V for value, and then D in the parentheses, kind of like those potential outcomes we saw before when we were thinking in our causal inference lens, except for here we're thinking about what would have happened on average in the population if I had treated everyone according to my treatment rule D. Now, not every rule is going to be good, right? I can come up with very, very silly rules. I could think of rules like, well, if you have brown hair, you should get treatment 0. And if you don't have brown hair, you should get treatment 1. That's an ITR, that's an individualized treatment rule, but that doesn't, necessarily help people have improved health outcomes. And so really, we're not just looking for any old function that maps from patient features to recommendations. What we're really looking for is how to get the right treatment to the right patient. We need some sense of optimality. And so this is going to be what we call an optimal ITR. It's the function that maps from patient features to treatment recommendations, so that when you calculate the value, the outcome you would observe if you treated people using the optimal ITR is greater than or equal to the value or the expected outcome you would see in the population if you used a different ITR. And usually we're thinking within some class of functions, which we'll denote by script D. Okay, so that's how we kind of get this idea of like right treatment to the right patient. Now, so far, I've, talked about right treatment, right person, but you might be thinking, Nikki, you've only talked about potential outcomes. Where is the data? So typically what we'll assume is that we've observed patient features and treatments and outcomes on, some sample of individuals from our population. Typically, the ITR framework has been developed where you have a batch of data, and we're going to try to learn the optimal ITR from this batch of data where people have been treated maybe randomly, like if you're in an RCT, or maybe just kind of how things are done in practice if you're in an observational study. And so then really the challenge is that people were treated according to kind of one set of way of doing it, maybe randomizing the treatments, and we want to find from that data a better policy, a better way to make recommendations. So we're going to assume that there's data. Don't worry, there's plenty of data here. And then, of course, to go from potential outcomes to data, if you're familiar with causal inference, we're going to need to identify these causal estimands, right? So the value function, remember, I defined it in terms of potential outcomes. What would have happened on average if we'd given everybody, treatment according to rule D? So to identify this potential outcome, this what would have thing to, actual data that we observed, we're going to need to make some assumptions. And these should feel very familiar to you if you've spent time in causal inference: consistency or SFdS, conditional ignorability, and positivity. And so once you do that, then we can go from potential outcomes to data. And once you have a data problem, we can do statistics. You might also be thinking, Nikki, you haven't said anything about time. Like, it's right, treatment, right patient, right time. You haven't said anything about it. And the reason why I didn't say much about time is because for the method I'm going to present today, it's a single stage problem. So we really just have one decision point that we're trying to make a decision at. But that's obviously not the whole universe of precision medicine. And there's plenty of methods that have considered how does time work, and plenty of framework for this. So I personally consider time to be one of the most powerful aspects of precision medicine, because the way that it works in this framework is we start thinking about what happens if you're layering treatments on top of each other. So, I give you a frontline treatment, but you fail it. Given your personal history, given that you failed treatment, given how your disease has evolved, when I'm at that second decision point where I need to figure out your rescue therapy or your second line therapy, I want to be able to account for all of that full history, and then make sure that whenever I'm making these rules that the treatments are working synergistically, or at least that we're not being myopic and making short-sighted decisions. So I actually think this is a very important part of precision medicine. And then the way that you would do this is that instead of observing features and actions and outcomes, at one time point, we'd observe them for people up to some time point, big T. People sometimes call this a dynamic treatment regime. And so the way that works is at each decision point, you have one of these functions that you're going to try to learn that maps from patient features to an optimal action. And then when you put all those together in a vector, you have the entire dynamic treatment regime for each time point. Again, you have to think about identification because all of this is being framed in the language of causal inference. And here it looks very similar. You have consistency in SFdS. We replace conditional ignorability with the sequential randomization assumption, and of course, positivity. Okay, so that is the precision medicine framework kind of in a nutshell. I'm going to say something that is my own opinion, and it's definitely a reductionist view of precision medicine. But I would argue that statistical precision medicine has focused on a few tasks. If you look at the entire literature, maybe looking back since like 2019 when Susan Murphy kind of wrote her seminal papers, Precision medicine is really focused on three things. The first one is estimation. So if you give me a treatment rule D, remember this is a mapping that goes from patient features to a treatment recommendation. We ask, can we estimate the value of it? What would have happened if I had treated everyone in the population according to this rule? Precision medicine has borrowed a lot of methods from, statistics and reinforcement learning. And so things that you might have heard of, methods that we've used for this are things like IPW, so inverse probability weighting. Certainly there's stabilized IPW, right? Augmented inverse probability weighting, G computation, G estimation, TMLE. There's all these ways that we can do this. So you have a lot of tools in our toolbox for doing that. The second question that statistical precision medicine has focused on is optimization. And that's the question where we say, can I learn not only, can I not only see how good would a particular policy be if I applied it to the whole population, but can I learn an optimal rule? What is the best rule that if I were to apply it, on average, outcomes would be better than any other rule I could, apply to this population, within some set of rules. And so here, there's a lot of methods, and I kind of refer to all of these as the learning methods. So you have outcome-weighted learning and, lots of little friends from outcome-weighted learning, backwards outcome-weighted learning, augmented, all these things. And then some of the tools come from reinforcement learning, Q learning, A learning, V learning, all of these different things are telling us how can we do this. And then the third question that a lot of precision medicine up to this point has focused on is design. What is the optimal trial design for generating data for precision medicine analytics? And what people, kind of the gold standard right now is the sequential multiple assignment randomized trial, or a SMART trial. And it's really where you have, it's in the name that you have multiple randomizations in sequence, one randomization for each key decision point. And because you're randomizing, you're eliminating, certain biases, certain confounding, and then you can learn these rules easily from those kinds of data. So, no need to worry about the specific methods that correspond to these different tasks. I just want to give you a sense of these are the things that people have focused on. This is my opinion, definitely kind of reductionist, but really estimation, optimization, and design. I like to take, or I believe that we should take, an expansive view of precision medicine. And I contend that we need to broaden as a field. And the reason why I think this is I think precision medicine is this way of generating evidence, a way of thinking about healthcare, a way that we think about, how do we actually, receive treatments, and it's often in sequence, especially if you're thinking about chronic diseases. And, it's this beautiful way of generating evidence, but people aren't really using it. And it can be kind of complicated. And we need to think about how can we make this evidence actually useful and actionable. So I contend, and I wrote this essay with Anna Kokoska at UNC, that we need to bring a systems lens to the entire evidence generation pipeline. And we call this systems aligned precision medicine. So not just thinking, very narrowly about these kind of statistical tasks, estimation, optimization, trial design, but really thinking about the entire pipeline and how it fits together, and how does this fit into routine care? How does this fit into the way healthcare is actually delivered and consumed? And then, of course, that's a very big picture. That's systems thinking. That's, lots of different stakeholders. That's implementation science. That's subject matter experts. That's your clinicians. That's your statisticians. I'm a biostatistician. And so I really want to think about how can I bring a translational statistical scientist lens to this field. And what that means to me is, how can I build tools for translation? So we can do estimation, we can do optimization, we can do trial design, but then how can I build new tools to help kind of bridge this gap to make precision medicine evidence actionable and useful and understandable and interpretable and all of these things that we often want when we're thinking about healthcare. Okay, so we have talked about, what is precision medicine. We have a little vocabulary, we have a little notation. And I hope I've, kind of set you up for thinking, maybe there's more than just estimation, optimization, and trial design, even those are all really important foundational things that we do in the field. So now I'm going to talk about a specific project, this individualized treatment rule characterization via a surrogate for the value function. We'll talk about what all that means as we go along. Okay, so here's our goal with this project is to characterize, that's goal 1, and find the optimal, that's goal 2, ITR. And I'm going to explain what this characterize means as we go along. And the strategy that we're going to use, and if we just have a one-sentence explanation, is I'm going to use a Gaussian process surrogate for the value function. Okay, so recall that the marginal value function for a particular treatment rule D in some class is given by this expression here, line 1. So I'll just walk you through it. So V of D, we already know that's the expected value we would observe if we treated everyone in the population according to treatment rule D. Okay, and that's using that potential outcomes language that we just went through a second ago. And then the second equality, remember when I said we can identify this thing, this kind of causal quantity, this what would have happened, we can identify it with the data, which means I can estimate it, which is what I want to do as a biostatistician, under some assumptions. And so, if you assume consistency in SUTFA and the conditional exchangeability and positivity, then we can write this as the conditional expectations you see on the right-hand side, the second equality. So we've gone from writing it in terms of potential outcomes on the left to in terms of the data on the right, which is awesome because once we have it written in terms of data, we have a statistics problem, which is something we can do. Okay, so the next line, is a little ugly, but basically it says, we're gonna suppose that we have a class of treatment rules D, ITRs, and they're a function of the patient characteristics X, and also they're parameterized by some theta. And we need our, theta to be bounded and finite. So you can just think it's compact in some R-dimensional cube or something. And so the second line is the exact same thing as the first line, except for next to the D, which stands for our ITR, which we've now said is indexed or it's parameterized by a theta. I've just stuffed the theta in there to really just hammer home the fact that we're thinking about these rules as a function of theta as well. And so that's all the second line says. And I just noticed I have an H1, that H1 should be an X. I switched the notation a little bit in the paper and then the slides didn't quite all get transformed. But anyway, same thing. I've just stuffed that theta inside the treatment rule D. So then if you look at it, then the optimal rule then, right? If my treatment rule is parameterized by a theta, my optimal rule is just I got to find the optimal theta. Once I do that, that's it. So really finding the optimal rule is finding the theta that corresponds to the optimal rule. And the way we do that, if you kind of look at it, we just need to find the theta that optimizes this value function here. So that's pretty nice, right? And I haven't done anything hard, right? I've just done the composition of functions. And now I'm saying, instead of thinking of the value function as a function of these treatment rules D, well, the D's are a function of these thetas. So I really just need to think of V as a function of theta. Okay, so this is really fantastic news because I have my value function and I can think of it as just as a function of these theta, and I just find the theta that optimizes the value function and I found the optimal ITR. Brilliant. The bad news is I don't really know what the value function looks like. It may not be differentiable. I may not be able to do some kind of like gradient descent or whatever I might want to do. So we're going to need to do just a little bit more work. So recall whenever we were talking about, kind of what are the tasks of precision medicine? And one of them was estimation. And so we have a lot of tools for point evaluating the value function for a particular rule D. And for each of these rules D in our world are parameterized by theta. So I have a lot of tools for figuring out what's the value for a particular theta. Remember, so we went through them: IPW, AIPWE, G computation, G estimation, TMLE. There's all sorts of tools out there that I can use. So the basic idea is we are going to sample some theta from our parameter space for the rules. And then we're going to evaluate or estimate the value function using IPW, AIPWE, TMLE, pick your favorite one. And so then we kind of have these sets of theta, which we're going to treat like our x's, and our estimated values that we'll think of as our y. And we have these pairs of these. And we're going to use a Gaussian process prior on these data to get a sense of what the entire value function surface looks like. So I've sampled at a few places. I know the thetas. I know their value. I'm going to put a Gaussian process prior on it to see what the entire surface across the parameter space, big theta looks like. So let me be a little bit more specific about what I mean. I'm going to pick some theta, and I'm going to use a space filling design just so I kind of get a good mix, all over the theta space to pick some initial thetas. Then I'm going to pick my favorite value function estimator. So maybe you're like, I love IPW, or maybe you think, man, G computation is my favorite. Pick your favorite one. I might have a little bit to say about what you should do, but for now, let's just say pick something off the shelf and get estimates of the value function at those thetas. And then we're going to fit this Gaussian process regression to it. So I've written that here at the very bottom of the slide. V of theta is modeled as a Gaussian process with mean 0. So we've just centered it at 0. And then we have a kernel function k. So what do we do now? I have some theta, and I have their corresponding v hats. I have this Gaussian process regression. What are we going to do? Well, remember, our first job, we had two goals here: optimization and characterization. Let's talk about optimization. So Bayesian optimization is a gradient-free way of doing optimization. And expected improvement is one of the methods in Bayesian optimization that tends to work fairly well. And it's fairly popular as well. And so here's what you do. All right. If you're not familiar with Bayesian optimizations, we have our Gaussian process, and we're going to use it to calculate the expected improvement. And that's this, kind of, it looks ugly and complicated, but it's actually very straightforward. Everything comes from the fitted Gaussian process. And so you calculate this expected improvement. It's very, very quick. And it's going to give me the theta where I think I might get the most improvement in terms of optimizing the value function. So it's saying, if you could only sample in one more place to try to find the optimum, where would you go? Where would I expect to find the biggest gain? That's what the expected improvement is telling me. So I calculate the expected improvement. I find the theta where I think that, this is really it. This is where I'm most likely to find the optima if I only, got to look one more time. And then I'm going to take that theta that the expected improvement function tells me that's where you should look, Nikki, and I'm going to calculate its v hat using my favorite estimator, IPW, AIPW, G computation, G estimation, TMLE, whatever you've been using. Okay, so now I have a new theta and its corresponding v hat. Well, the great thing about a Gaussian process is it's conjugate, right? We can keep updating it quite easily. So I'm just going to update my value function with my new theta that I just was suggesting me, my new v hat, update my my Gaussian process, and then I go back to the expected improvement. I say, okay, well, now I have a little bit more information. I have a slightly better Gaussian process regression because I've added a little bit more to it. Now I'm going to ask again, where should I go next if I want to find the most improvement? That's what expected improvement is telling us. Expected improvement says, okay, Nikki, here's a new theta. This is where you're most likely to find the optima. Take that new theta, calculate my v hat using my favorite estimator. I have a new theta, a new v hat, update the Gaussian process. And I keep doing this process until the expected improvement from sampling one more time is small, I've met my sampling budget, or I just get tired of doing it. Okay, and so that's the process. It's straightforward on how to do the optimization step. So that was task one, and that's how we're using our Gaussian process to do that. And this is why I call this, using a Gaussian process surrogate for the value function, is that I'm really using this Gaussian process as a way to try to understand the entire value function without needing to know it explicitly or doing anything too complicated. The second task, though, that we had was the characterization task. And so what we're going to do is we're going to use the posterior predictive distribution of the Gaussian process regression to characterize the entire treatment rule parameter space, i.e. all the value for all the treatment rules in script D. I think this is easiest seen using the simulations. So we're going to talk about this more whenever we look at the simulations, which is what we're going to do next. Okay, so let me, orientate you to how we did these simulations. So you'll see here, we have beta naught and beta 1. These are the parameters of the treatment rule. So this was theta. We were using theta earlier, so you can think of that as theta naught and theta 1 if that's easier. And on the shading, if you were to take any, sorry, let me go back. If you were to take any beta naught and beta 1, right? And this is a 2-parameter ITR. These 2 parameters completely, define the ITR. And then what happens is, the way we've colored it is, if you were to take where beta naught and beta 1 meet, right? So that is a particular pair of beta naught and beta 1. That corresponds to a particular ITR. And then, because I wrote the simulation, I know what the true value is. I've colored the background of these graphs to correspond to the true value for that particular pair of beta naught and beta 1. So for that particular ITR. And so you'll see the lighter regions have higher value and the darker regions have lower value. And so if we were thinking about what would we want if we were to learn an optimal ITR, is I would hope that when I plot it's beta naught and it's beta 1, and I plot it on this graph, I hope that point lands in a light colored area, yellow or light green. And I would hope it would not go to one of these darker colored areas, the dark blues and the purple. And of course, we did this with kind of 3 different levels of noise. And so that's why we have 3 different panels, the 0.75, the 1, and the 1.25. All right, so that's the setting. So we have a 2-parameter ITR. And if we think about, if we were to take the parameters and see where they meet on the graph, the underlying values is the true value, like what would have happened if I treated everyone according to the policy that corresponded to that beta naught and that beta 1. Okay. So here are the results from the simulation for optimization. We used 4 different value function estimators. We used AIPWE, which is in the first column. We use G computation, which is the second column, IPW, and then stabilized IPW. And remember, we said if we were to plot, what the simulation thought was optimal, we would want it to land in the light colored areas. And you can see here, AIPWE does a pretty good job of setting it there, in those light colored areas. IPW, great. Stabilized IPW, we're really hitting it. And in the paper, we actually did some more calculations to quantify this, but I think the picture is really nice because, you kind of see what your target is. I want to land in the yellow areas, and you can see that whenever we plot them, they get there. And each of these had 1,000 simulation runs. So, we did this 1,000 different times, each time plotting one of these circles where it thought the optimal was, and it did exactly what we wanted it to do. You are probably, though, looking at G computation and thinking, oh my goodness, Nikki, what on earth happened there? G computation failed miserably. And the reason why G computation failed so miserably is because we wrote G computation using very simple linear regressions. We didn't do anything really fancy. We wrote down the simplest kind of linear models that we could. And because the true value is not linear in the parameters of the ITR, it just failed. Like, it did a really terrible job. So I said earlier, pick your favorite value function estimator, but really, G computation, you have to define the models quite explicitly. You're estimating these conditional mean models, so you need to know what that regression looks like. If you don't feel strongly that you know that, G computation is probably not the best choice. And I would actually recommend using something like an AIPWE or an IPW, just because you don't have to specify the model so much. So, we could have gone back and made different modeling choices for the G computation, but I think it's a good lesson here that this is a really nice strategy, something that you could use in practice, but we really rely on having a good value function estimator. And if you don't have a good value function estimator, things can go awry very quickly. And we saw that in the simulation with the G computation. So, but otherwise, using expected improvement, using Bayesian optimization, using this kind of Gaussian process approach to getting an optimal, really nice results when we had a nice value function estimator. Okay, so that's the optimization task, and so it seems to be working pretty well. And the second thing, and this is the thing that I really haven't said anything about, I just keep saying, we're going to do this thing called characterization, but I haven't told you anything about it. So here's the picture. So this is one of our simulation runs. So on the previous slide, on this one, this is showing the results after we did it 1,000 times in each of these different settings using these different methods. We're thinking about the picture on the far right. So this is the truth is on the far right. But I just took one single simulation. And whenever, we asked, in this simulation, we got the optimal rule out, that's where this red star is. So if you take the red star and you go out and you look at your beta naught and your beta 1, that would have been the optimal ITR that I would have, published if I were writing for a clinical journal. I would have told my, clinical partners, I said, you know what? The best way to treat people is, with the rules, with the parameters that correspond to this red star. And that's all the information that I would be able to give them if I was just doing the optimization task. But remember, I really feel strongly that we should be more translational. We should really think about where these rules are going to be used and how they're going to be used. And what we've done here is, this is not the truth that's colored on the background. So this is not what you saw on the far right slide here, or the far right panel here. What this is the posterior predictive distribution for the Gaussian process after I've done the optimization piece. So this is my surrogate for the value function for just this one simulation run. And by doing this, and then color coding it, kind of using the same kind of scheme where lighter colors are better, I can see that my optimal rule certainly falls in a region where my surrogate for the value function says this is a good region. But there's also this other region that's also yellow. It's also light. It's also optimal. It might also give me similarly clinically important differences or changes for the patient. But if I had only done the optimization piece, I would have missed this completely. Now, you might be thinking, well, it doesn't matter, you found something that's really good. But then when we start thinking about how things are done in practice, maybe, I don't know, maybe the rule that we learned that was optimal, that's in that left-hand yellow region, is really hard on patients. Maybe they don't like it. Maybe clinicians don't prefer it. Maybe it requires a lot of resources and it's a low resource setting. It might be easier, more feasible, more realistic to use a rule that comes from this other yellow region. Maybe it's less resource intensive. Maybe it's easier on patients. if we hadn't have looked at the posterior predictive distribution, if we hadn't have checked, where there might be multiple optimal, we would have missed this completely. And I think, this gets us towards that idea of like, how can we really be thinking about where these rules go and how we use them? How do we translate them into action? Is that certainly, of course, we want to do the very best, but there might be multiple rules that give us equal or very similar clinical benefit. And then at that point, we really want to start thinking about, how do we make this easy? How do we make this realistic and feasible for patients, providers, and their caregivers? And so that's what I mean by characterization, is not only can I find you the optimal rule, but I can give you the sense of the entire treatment rule space, thinking about, what's that value function look like? And we can really have these conversations with our clinical partners and our patient advocates and caregivers about like what makes sense for that particular person. So that's characterization. And then the next thing I want to talk about is we've applied this to a specific setting, chronic limb-threatening ischemia. So CLTI is characterized by wounds, or let me go back. CLTI is a vascular disease, and it's caused by abnormal narrowing of the vessels in the leg. So if you have coronary artery disease, you have ischemia in the heart, so abnormal narrowing of the arteries of the heart. Sometimes this is due to like cholesterol or other things like that. And so we'd say you have cardiovascular disease. If you have this in your brain, we would say you have cerebrovascular disease. And then, of course, if you have it elsewhere in your body, typically in the legs, because the legs are far from the heart, we say you have peripheral artery disease. And then chronic limb-threatening ischemia is the worst form of this disease. It's a very severe, advanced type of peripheral artery disease. And it's characterized by wounds, ischemic breast pain, foot infection. And there's all sorts of treatments for this. So if you have a foot infection or you have a foot wound, you need to get wound care. You also need to have your comorbidities managed. So there's medication management. And then you can do revascularization, which is a surgery. Either they'll put a stent in there to try to hold that artery open, or they'll do a bypass where they take another, vein and they try to actually just go around the narrow part of the vessel. These patients are incredibly complex. So you imagine that if you have narrow arteries or clogged arteries in your leg, you probably have clogged narrow arteries elsewhere in your body, where there's a lot of diabetes and kidney disease, hypertension, hyperlipidemia, hypercholesteremia. These are very sick patients, and they're very complex. And the outcomes are not great. So like 25% of them will have a major limb amputation. So that's a below or an above knee amputation within 2 years, and up to 50-60% die within 5 years. So very, very sick patient population. And very often when patients come in with these wounds that won't heal, and they're not healing because there's just not enough blood flow to get to that wound, physicians have to decide, do we try to heal this without surgery? Will it heal without surgery? Or do we go ahead and do one of these revascularization procedures? But remember, these are very sick patients. So there's all these additional surgical risks associated with that. And, really what we'd like to know is, how can we give surgeries to the people that it's not going to heal without surgery? And then how can we avoid surgery in people that it would heal with just wound management? So there's a lot on this slide, but we had some data from UNC of a cohort of EHR data linked to the administrative scheduling data from a wound management clinic. And the question was, for patients that had one of these wounds, after a month of a trial of wound care, you kind of have to make a decision. Is the wound getting better? Is it healing enough that we would keep doing this non-invasive kind of wound care or less invasive kind of wound care type stuff? Or do we go ahead and make the decision to do surgery, to do revascularization? And so the way that we're going to look at our treatment rules, we're going to look at compliance to wound care in that first month, where we're just trying to heal it using wound care. And we're going to look at the size of the initial wound. So we'll denote compliance with a C naught, and the initial wound size is a W naught. And so this is, what we're going to use to make our decision about this after, having tried wound management for a month. How are we going to decide if you should keep getting wound management or if you get surgery? the outcome we're going to use is the wound healed, is the patient alive, and is the limb intact 6 months after the initialization of wound management. And this is what the treatment rule class looks like. It's just a simple indicator function that says, you should do revascularization if the compliance during that trial period was less than theta 1, or if the wound was bigger than theta 2. And so here are the results. The estimated rule is shown by the white star. And so the optimal rule says that if your compliance was less than about 45%, or your wound was bigger than 6.95, so about 7 centimeters squared, you should just go ahead and get revascularized after a month of wound management. However, and if you were to do this, then we would expect to see a 14% improvement on our outcome of being alive with the limb intact and the wound heal at 6 months, compared to what we just observed in this patient cohort that we had available to us otherwise. So, I've denoted the optimal rule of that white star. And so that, if you would take the white star and you go down to the 2 parameters, that's the optimal rule. But I've also, in the background, colored it what the posterior predictive distribution looks like across the entire ITR parameter space. And we can see there's actually a whole kind of range, a whole swath of rules that fall in this dark red regions that are these rules that give us very similar clinical benefit, which means there's some wiggle room. It tells physicians that, maybe you were just, your wound is kind of close to 7 centimeters squared, how far off from this 6.95 do we need to be that, to change practice? What if a patient comes in and they were, 40% compliant, or they were 50% compliant? How does that work? Do I still get the same benefit? Do I still need to use these exact cutoffs? It gives a little bit more flexibility to physicians. This is also a nice way for them to say how important compliance is to that initial round of wound care. If you don't go to wound management, it's probably not going to help you heal your wound. And so I think this is lovely and excellent, is it really kind of helps us understand things that are not on the edge, or things that are edge cases. What do we do in those situations? It also can help provide some understanding about the different roles of different behaviors in outcomes. Okay, so we're just about running out of time here. So just to conclude, precision medicine is this very promising framework for generating evidence to improve health and healthcare. For me, my belief and what I hope you feel inspired is that realizing the promise of precision medicine will require cross-disciplinary collaboration. So we really, need to think as statistical scientists, how can we help to build these amazing statistical tools that we have, but how do we move them in the translational pipeline towards practice, towards when we're thinking about evidence synthesis and how we're building guidelines for treatment? I think that statistical leadership is critical for this, and that statistical methods can drive translational innovation. And so I hope that you feel excited and empowered that coming in as a statistician is really important for improving health and healthcare, and thinking about what could evidence look like in the future, not just how do we make more evidence that looks like the evidence that we already have. Alrighty, so I'm just about done, but I want to make sure that I thank my co-author, Sydney Browder, who did a lot of the data cleaning for us for the data analysis. Kate McGinnigal is a vascular surgeon at UNC, and then Michael Kosarok, who also provided a lot of support and help on this. We're always thankful for funding. And then, of course, many thanks to Nicolas and Louise and Sandrine for setting this up and making sure I knew where to be, and for being here and all this amazing stuff. So many thanks to them for the invitation. I co-lead the Precision Health and AI Research Lab with Michael Kosarok. So I put our logo there, and you're welcome to look at our website to see what some of our students and postdocs and faculty scholars are working on. And you're certainly welcome to message me, email me if you have questions or thoughts. And that's it. Thanks so much.
Thank you very much, Nikki, for this very inspiring talk. I've seen there's no question on the app, have just one question to ask you. In your opinion, what are the main challenges in precision medicines on the statistical point of view and on methodological sort of view? Huge question. Just one, but huge.
Yeah, okay, like we could like write books on this. So I think one huge problem in precision medicine is it's actually linguistic. Is precision medicine is a huge field, and you have people working kind of in mechanistic solutions. You have people like me that are working on data solutions. And there's a lot of miscommunication and talking past each other because we're using the same words, but we mean different things. And I think that slows us down sometimes. And we also say, well, that's not what I'm doing. I'm doing this other thing. I think there's a lot of space for synergy and working with our partners that are using different methodologies and to bring them all together. I would say statistically, we've spent a lot of time learning how to estimate these optimal rules. We still don't have a really great sense for doing inference. So we can do inference for the value function, which is really important and great work, and it's very hard. If you can't use standard asymptotic arguments because of that max operator. When you take the optimal, it actually just things don't work quite as well, so it's quite complicated. But doing inference for like the individual treatment recommendations is quite hard. And Nicolas, you know this already, but one of your students is working on this problem and has a really nice Bayesian solution to kind of bring forward or advance forward the inferential potential that's here.
Thank you. There is a question. Thank you very much for the presentation. Can you precise the number of observations needed and number of covariates that can be taken into account for the decision rule, please?
Yeah. Oh, man.
Very practical question.
Yes, very, very practical. Okay, so there's a couple of ways to do this. So what I presented today, these Gaussian processes and using Bayesian optimization, the kind of stuff I showed you, usually kind of tops out at 15, 20 covariates. So not terrible, but not great. You need to come in with some outside knowledge of what's really important. Beyond the work that I presented, there's people that have done work with, much higher dimensions, and you do some variable selection, and, you can really kind of start thinking about, these very high dimensional spaces, looking at low dimensional manifolds or just kind of low dimensional subsets of covariates. So I wouldn't say like problem solved, but there are solutions out there. The sample size problem is really quite hard. And this kind of goes back to thinking about inference, because it's, we don't, if you were going to like power a study to learn an optimal ITR, it's not power in the traditional sense. And so what that means makes it a little bit more open to interpretation, and it can be difficult to say definitively. And you often do just a lot of simulation studies to try to get a sense of how these rules are going to work and what you think your population is going to look like. So I know that's an unsatisfactory answer, but that's kind of where we are, where there's not like hard and fast rules about what you would need. It certainly depends on the signal to noise ratio in the data and the population that you're studying. And there's, if you want to work on this, there's plenty of open questions about sample size.
Thank you very much, Nikki, for this very nice talk. And to congratulate you again, and thank you again for accepting our invitation for this webinar. And there is further events organized by the Biopharmacie and ILS group in the next few months. Thanks again, Nikki. I think there is a capture of the webinar, so you will find it elsewhere. So see you soon, and thank you everybody for coming to listen to Nikki. Thank you. Bye. Bye, Nikki. Thank you.